Okay, this is a quick video about how to calculate the center of mass. It's not a video about why center of mass is an interesting concept or extremely useful to physicists or about conservation of momentum. I just want to know, what is this? What is this? How do I use it? When do I use it? Okay, first of all, let me just say that this is an average. Essentially, you want to know, on average, where is all the mass in your system? For a continuous distribution, you look at something that looks like this. One thing I'll point out, this is a vector, because it tells you a set of coordinates. There's an xcm, a ycm, and a zcm. In other words, I want to be able to point in space to where the average location of all the mass is. So what I'm finding is a vector, xcm, that has those as its coordinates. Okay, so let's set this up. We'll see how we use it. This is going to be a rather calculational video. It's not particularly interesting, but I think it'll be useful and it'll help you solve some of the problems you get. Okay, so let's look at the easiest case. 1D particles. Okay, that means there's no y or z direction. There's only x's, and so if I want to apply this formula, really what I'm looking at is adding up each of the individual masses and their actual position. So that is, I only have x's to consider here, and I add them all up. So let me just show you what that looks like. This guy is m, and it's at 0. So I put m times 0, m1, x1. This guy is 2m, and it's at x equals 2, 2m, 2. And in the bottom, I just add up all the masses. You get the idea. If I do all that, I'll end up with x equals 3.6. What does that mean, 3.6? Well, that's the average of where all the mass is. That's somewhere around here. And actually, yeah, that kind of makes sense, because I've got a lot more mass, 5m, over here than I have over here. If it bothers you that it's 0 here, and you're like, wait a minute, it's like you're not counting it. No, I am counting it because it's weighting it more towards 0. It's making it a smaller number. So this is on average where the mass of my system is. That's what the center of mass is. Let's look at a more complicated example. Okay, now we're in 2 dimensions. Oh boy. It's actually the exact same problem. I just have to do it twice. When I do this, notice that the center of mass in the x direction only cares about x's, and the center of mass in the y direction only cares about y's. So when I go to calculate these things, even though there's 2 numbers here, when I do the x's, I only care about the x coordinates. I only care about the x coordinates. And when I do this one, I only care about the y coordinates. This, if you understand the other one, is basically the same problem. There's really not much new to talk about here. Okay, let's calculate it out. We get a final answer. We get a coordinate, right? 3.1.6. What does that mean? That's somewhere around there. Well, if you think about it, most of the mass is around here, and so this makes it lower, this makes it higher, this makes it lefter, this makes it righter, and this guy wins more than the others. So yeah, that's about it. That's where the center of mass is and how you calculate it. So now let's get crazy. Okay, here we go. 1D continuous. So here's my formula. It should still work. The problem now is I have one end at x equals 7 and one end at x equals 2. I never had that before. I always said that the particle was in one place. Now it's in 2 places. What do I do? This is a bit of a problem. So what I'm going to do instead is I'm going to say this bar is not really one thing. This bar is lots of little things. And I'm going to add up all of those little things together. And I'm allowed to do that so long as I keep the little things very small. In other words, if I make this piece so small, its left edge and right edge don't really have different positions. It's essentially in the same place. If that bothers you, think about what you did in your calculus class. That's actually the claim you make all the time. In the limit that dx approaches 0, you say that some function has the same height at 2 different values of x, so long as they're dx apart. I'm just saying the same thing. The distance along the rod is the same on both ends of these, so long as I allow dx to be really small. Of course, if I have a very small dx, I'm going to end up with a very small dm. Another way to say that is that dm is mass per unit length times length, right? Well, I'll have a really teensy bit of mass if I have a teensy bit of length. This guy lambda is a bit of notation, totally standard, what physicists like to call mass per unit length. Lambda sounds like length, so we use that. For area and density we use, and volume density we use other Greek letters, which I'll show you in a second, but it's really just a bit of notation. Okay, so what do? We have to make a bunch of these little things and talk about each little bit of dm at each different x, and then we add them up. Only instead of m sub I, they're dm's. They're all the same mass, and they're all really tiny. and I have some variable that changes. If you think about this, though, you're going to have to add up an awful lot of these, in fact, an infinite number of them, and doing an infinite sum is a drag. Fortunately, somebody figured out a quick way to do it, and that's called an integral. Apparently, an antiderivative is the same thing as an infinite sum. You learned that in your calc class, of course, right? Okay, so what do? I just plugged in for dm. Instead of dm, I wrote lambda dx. Up here, I need to multiply by an x, because there's an x here, so I threw an extra x up top. On the bottom, it's just the integral over dm, so I just plug in lambda dx. Okay, so this gives some number. Now you might say, wait a minute, what's lambda? What do I do about lambda? Okay, there are two cases. One is which the bar is uniform, in which case I have a value of lambda here, and I have a value of lambda here, and it's the same. The bar looks the same everywhere. So if I want to know how much mass per unit length there is, it doesn't matter. I take the total mass, divide it by the total length, and it's just some number. The other case is it's not uniform. And if it's not uniform, somebody needs to tell you something about the bar. You can't just say, go find the center of mass of this non-uniform bar. You'd say, well, how is it not uniform? In what way, right? I'll talk more in maybe another video about how you don't even need to do math in order to find the center of mass of a crazy bar, but that's a different topic. Okay, let me show you two examples side by side. One, the bar is uniform, the other bar is not uniform. This is what the problems would look like. Okay, find the center of mass of a uniform rod of length 5 meters and mass 10 kg. And this one, find the center of mass of a rod that's 5 meters long but has a non-constant density. Okay, so what I'm going to do, I'm going to get rid of the numbers and just put an M and an L because I don't feel like doing numbers anymore. And I'll just say lambda is total mass divided by total length, M over L. So what do? I plug in for lambda, I shove in my x, that's all I'm doing, lambda x dx. Where do I integrate from? Well, I go from x1 to x2, but I think it'll be instructive. Let's just pretend that x1 is 0, and if the bar is length L, that would make x2 L, and so I go 0 to L on both integrals. I do the same exact procedure here, except instead of plugging in M over L, I plug in x squared. So it's lambda x squared times x, you get x cubed. Okay, if I do this, I'll get L over 2 here, and I'll get 3L over 4 here. Does that make sense? Well, if it's uniform, where do you expect the center to be? Center of mass should be in the center. That's the average location. If it's non-uniform and the mass gets bigger, in other words, this thing maybe gets heavier and fatter as I get toward this end because it increases like x, well, then yeah, I expect to find it closer to that end. So this makes sense. This is about as hard as it gets when you're in one dimension. They can give you weird integrals to do, but from a physicist's point of view, I just plug it into your favorite online integrator. It doesn't matter. Okay, now it's going to get real. This is where things start to get a little difficult. There's a limited number of cases of this that we can look at in a class where you're not required to know multivariable calculus. I'm going to show you the formula you come up with, and if you know multivariable calculus and that's your thing, you are set. You can go to town doing double and triple integrals. If you don't like double and triple integrals, I'm going to show you a couple of examples that you can do without knowing multivariable calculus, even though technically that's what you're doing. Okay, so this formula still applies. So I still need to know dm, and dm looks different. If it's a area, then dm is mass per unit area times area. If it's a volume, then it's mass per unit volume times volume. In other words, instead of breaking up a line into tiny slices of a line, a cube is made of tiny cubes. Each cube has a mass dm. A square is made of tiny squares, and each square has a mass dm. So what does that look like? Here, dm is sigma, so that's what we use when we talk about the mass per unit length, mass per unit area, excuse me, that's just a bit of notation. And then rho is what physicists like to use when we talk about mass per unit volume. So strictly notation there. And then what's volume? Dx, dy, dz, because I have to go this way, and I have to go this way, so I'm adding up the wrong dx, and then I have to go into the cube. I have to go in this direction too. I have to do all three directions. And so this sets me up in a position where for this guy, I need 3 integrals. And for this guy, I'm going along this direction. I got to add up all the boxes, and then I got to add up all the boxes in this direction. I got to do an integral that way too. So yes, you have double and triple integrals. They don't look pleasant. The truth is there's a lot of cases you can do without really even understanding what these triple integrals are. I'm going to switch up the notation really quickly one more time just to make it a little easier to write, but also just to say it's not so much dy, dx, dy I'm interested in. What I want to know is, what is dA, the area of that? And the reason I do that is, I don't know, if I have a sphere and I want to work in spherical coordinates, well, maybe I don't want to use dx, dy anymore. I can use spherical coordinates. More than that, though, for these next two problems, I'm going to show you what I really mean when I say it's dA that's important, not dx dy. Okay, so here I have two examples. One of them is an inclined plane. What would a physics video be without an inclined plane? And notice for the inclined plane, this is a 2D case. And for 2 dimensions, I have mass per unit area is mass over area. And my little tiny bit of mass goes like sigma times dA. There's that dA guy again. Over here, I've got a pyramid, which is kind of like a 3D inclined plane. And notice I have dm is rho dv, and the extra little bit of spiciness on this problem is, ooh, I gave a non-uniform rho as a function of z. So we're going to solve both of these problems, and we're not going to have to use fancy multivariable calculus to do it. We're going to use a technique called slicing, which you can't always do, but you can do in an awful lot of cases. And I'm going to show you how that works. Okay, so first things first. Our formulas for the center of mass are exactly the same as they were in the last slide. Somehow I need to figure out dA, and once I know dA, then I find xcm by integrating x over dA, and I find ycm by integrating y over dA. What's dA in this case? Well, it's dy dx. And the thing here is I really don't want to have to do a double integral, so I need to express dA in terms of one variable. Well, one way to do that is to say that, look, this triangle is actually made out of a bunch of rectangles. In other words, I slice the triangle into a bunch of little rectangles, and what do? I integrate all of those little rectangles over the entire length of the triangle. So now what I'm doing is a 1D integral along x, and what is it that I'm integrating? I'm integrating the area of each of these rectangles. Now you might say, hey, that's kind of funny. How come you chose to go vertically? Could you also slice horizontally? 100%. I could slice horizontally. And then in that case, each one of these little rectangles has a length x and a height dy. So if I use the horizontal rectangles, I'm going over y. If I use the vertical rectangles, I'm integrating over x. So which do I use, and what's the advantage? Well, one of the things we have to keep in mind when we do slicing is that we need things to be constant over those slices. So for example, if you look at the xcm integral, I have x inside that integral. I want to pick slices for which that x is a constant for each slice. That means that for this guy, I want to use vertical slices. Look at this guy. This guy has a y in it. So for the y, I want to use the horizontal slices. So let's amend these integrals using those different slices and see what that looks like. If I punch that in, then here are my horizontal slices. There's my x dy. Here are my vertical slices. That's my y dx. Now, the thing to keep in mind here that's a little awkward is, oof, I've got an x and a y dx, and here I've got a y and an x dy. I don't know how to do that. So what I've got to do is actually get rid of one or the other. So let's just look at our vertical slices. My vertical slices here certainly have a width dx, and what is the y value? Well, look. The y value is whatever the top of the triangle is. This is just a straight line whose formula is y equals h over L times x. That's the equation of that line. That means that I can just substitute that in. It's really not a big deal. Okay, how about for this one? For this one, I have a horizontal slice, and I need the value of x. Now, it's tempting to say, oh, well, maybe x is, maybe x is L over h times y. But there's actually a small problem there, and the problem is that when y is 0, that says x is 0. And that's not true. Look, down at the bottom, my horizontal slice is actually the biggest it is. So what I need to do is be a little bit more careful and say that x is actually L minus L over h times y. If I do that, then when y is 0, x is L. Okay, that looks great. And then x decreases linearly, and when y is equal to h, x is 0. Okay, that is nice. So I can punch those two both in. If I punch those two both in, I end up with two, I don't know, not terrible looking integrals. If you punch up the value of those integral, you end up with those as your final answers. So here I get 2/3 of the way. Here I get 1/3 of the way. Does that make sense? I don't know. I'm looking around here, and the question is, let's say that that's the halfway point, right? Clearly, there's less mass above the half than there is below the half, so I expect the y center of mass to be below the halfway point. And yeah, okay, this is below the halfway point. On the other hand, if I look at the x, the farther I go to the right, the more junk there is. So if I cut this in half,
I guess I expect it to be farther over. And so, yeah, this actually does make intuitive sense. It's farther to the right than the midpoint, and it's lower than the midpoint in the y direction. So that actually squares. Okay, now let's move on to the 3D case.
So for the 3D case, I'm going to do the exact same thing I did in the 2D case, and that is slicing. Remember in the 2D case, what I did was I made these little horizontal slices, because over those horizontal slices, y was a constant. Well, if I make horizontal slices in 3 dimensions, that means making little squares. And for each one of those little squares, z is a constant. So what's dv in this case? dv is the area of those squares, a, times dz. And what's the area of the squares? X times y. So you could think of each one of these as having a little bit of height, dz. So the advantage of slicing horizontally is that on a horizontal slice, z is a constant. So what does this mean? This means that dm goes like rho dv, as it normally does. Instead of dv, I write xy dz, and then instead of writing rho, I write z squared. Why? Because that's what the problem tells me. Easy as pie. Now the only wrinkle I have here is that somehow I'm supposed to integrate over dz, and I've got an x and I've got a y. That's a little awkward, but remember, we had the exact same problem over here. All we need to do is come up with some formula to get rid of it. And we've actually already come up with that formula. If you recall for this case, we said, how do we parameterize? This, in this case, notice that the area gets smaller as we get farther up, and that was exactly the same problem we had in the horizontal slicing. In this way, we solved it by saying L minus L over H times Y, right? We're going to solve it the exact same way in this case by saying that X equals Y, meaning the pyramid is a square, and then that's L minus Z cotan theta. You might say, hey, that looks different than before, but remember, L minus L over H times Y, holy Toledo, that actually is cotan theta. In other words, this 3D problem is an awful lot like the 2D problem we just did. Now remember, I'm slicing horizontally because I want slices over which my density is constant. So what does the z center of mass look like? Well, it looks like that awful triple integral we had on the previous page. You might say, wait a minute, what about the xcm and the ycm? Well, look, I don't need to do anything in order to know that. I could split this guy right down the middle in these two directions, and I know that somehow the center of mass is going to be in the center. The question is, how high up the pyramid is it going to go? And notice that since I have a z here, that gives me yet another reason to be integrating over z. I need to make slices where the things inside my integral are constant. And if I make my slices dz, that will be the constant in that case. So if I make my substitutions, I end up with something a little bit uglier. And I don't feel like doing the integral. You can do the integral on your own, and you can find out, I don't know, maybe it's up here. It's hard to say, like there's more junk down here than there is up here. But look, the density increases as you get higher. So I actually don't know where it is. I'm tired of doing integrals. I don't want to do any more integrals today. But the key technique in this part for multi-dimensions is slice the object along planes of constant density. So slicing for 2D means making little rectangles. Slicing in 3D means making bigger rectangles, bigger squares. Okay, hopefully this video was more helpful than confusing.